Consider a vertical coordinate system where g is pointing downward, and the particle is located initially at x naught and y naught. If the particle is given initial velocity v naught, the two initial velocity components will be called v naught x and v naught y. And as time passes, the particle reaches its highest point, and that's where the Vy component becomes equal to 0. So, what happened here? We all know that gravity exists only in the vertical y direction and points downward. Why? Because if you release a ball from this height, it will fall down vertically, not horizontally and not to the side, only vertically downward. This tells us that the acceleration in the horizontal direction is equal to 0. And that's also why the Vy component of the velocity reduces as we go up until it becomes 0 at the maximum y. Remember the turnaround? Same thing here. But since ax is equal to 0, Vx remains constant all the time. And as the projectile falls down, it makes a symmetrical motion path with Vx constant and Vy is equal and opposite to Vy from a point on the other side at the same height. Same here, Vx constant, Vy is equal and opposite. And notice here the increase in the value of Vy as it falls down from the maximum height. Assuming positive direction up, our three constant acceleration equations are given here with a as negative g and s replaced by y. If we use the three equations in x, the first and third equations will give us a trivial solution, which is Vx equals v naught x, which we've already explained. So the only calculation that can be made in the horizontal direction comes from the middle equation with a equals 0, which is x minus x naught equals v naught x times t. So let's say you have this projectile launched from A with v naught equals 4 meters per second at 60 degrees from the horizontal. The x component of velocity remains constant until it hits the ground at B after covering 20 meters horizontally. And let's consider another situation where the particle moves on the ground with constant velocity of 2 meters per second and also covers 20 meters. In both cases, Ax equals 0. And we can use this equation, as mentioned before, to calculate the time, for example, for the constant velocity given and displacement covered. How about symmetry? How can we take advantage of the symmetry in projectile motion? If the projectile is launched, reaches its maximum height, and returns back to its same height, the motion is symmetric with half distance and half time covered as shown. And since Vx remains the same and Vy is equal and opposite, the magnitude of the final velocity will also be the same, with the same angle pointing down instead of pointing up like the initial condition. Let's see how can we use symmetry. The third equation confirms our conclusion about symmetry. This part goes away, and just take the square root of both sides, and consider the solution with the negative sign. Why take the negative sign? Because it means Vy is equal to Vy naught, but opposite in direction. And that's what physically happened. So by going to the first equation and using negative Vy naught instead of Vy, and using delta y equals 0 in the second equation, we end up with two equations. But if you look carefully at both equations, they are exactly the same, and they both result in this simple formula in the y direction, which you can combine with this formula in x and solve any symmetrical projectile problem. Consider the situation where the projectile is launched 2 meters above ground with V0 and lands after covering 3 meters in X. The question is, does it make a difference if we take our datum from the projectile's initial level or from the ground level? Let's see. If the datum is taken from the projectile's level, the initial y will be 0 and the final y will be -2. And if the datum is taken from ground, the initial y will be 2, but the final y will be 0. And in both cases, the left-hand side of the equation does not change. It's always delta y equals -2. Why? Because the projectile's net displacement is 2 meters in the negative direction, regardless of where you put your datum. And as for delta x, it is plus 3 meters, since right direction is our default positive assumption. How about if the positive direction is taken from the projectile, but assumed down? Simply, all equations should be assumed positive down. For example, in this equation, y0 now equals 0, and final y is positive 2. However, note also that v0y is pointing down, which is positive, and g is also positive in this case. What if the projectile does not land on ground, like in this situation, for example? No problem. You just need to identify its final location as follows. If we take the positive up from ground, you can see that the initial y is 2, and the final y is d sine theta, or delta y is equal to d sine theta minus 2. And note that delta y here will be negative because the net displacement is against the positive direction. As for the displacement in x, we only need to add d cosine theta and end up with the total delta x.